So I'm going to talk about a classy sample correctors. I want to thank Clement and G, who I don't think G is here, for inspiring this title, the classy part of the title anyway. So there's been a lot of work over the last 15 years on testing properties of distributions on very large domains. Given samples of a distribution, you might want to know things like what's the entropy, how many distinct elements are in the support of this distribution, what's the shape of the distribution, is it a monotone distribution, is it bimodal, is it close to the uniform distribution, or is it maybe a Gaussian? I mean, many times people do things assuming their distribution is Gaussian. How do you know if it's Gaussian? How many samples do you need to determine this? Is it Zipfian? What about, let's say you've determined that it's Gaussian, what are the parameters? So there's lots of questions people are interested, and these are kind of basic questions considered in statistics, information theory, pretty much everything needs samples and needs to know things about their distribution. So the key question that we've all been looking at in this community is how many samples do you need in terms of your domain size? And there's really been a lot of work on this problem. The main issue is, do you need to estimate the probability of each domain element? I mean, there's a sort of famous plug-in estimate, which essentially what it says is you estimate the probability of each domain element, and then for your estimate of the distribution, you decide what properties it has or what sort of distribution it is. And our question in the TCS community is, do you need linear in the domain size many samples? Do you need to actually estimate every domain element? Or can you do something faster if what you want is a weaker guarantee? Okay, so the question is, can the sample complexity be sublinear in the size of the domain? And this, of course, rules out standard statistical techniques. Here it would be the normal model or the typical model. You've got some distribution, you know nothing about it. It's essentially a black box. What you're allowed to do is press a button and then you get a sample. That's it. Okay, so you press a button, you get a sample. You press a button again, you get another sample. Okay, and this is some distribution over a domain. Let me just call it the numbers 1 through n right now, but it could be any domain. It could be a domain that has some sort of metric associated with it. It could just be arbitrary names. So let's call our domain 1 through n, and this thing generates IID samples. So every time I press the button, my sample is completely independent of my previous sample. Okay, and we'll use P sub I to be the probability that the distribution P outputs domain element I, but we don't know these P sub i's. These are the underlying probability distribution. We just don't know them. And for any type of problem we're testing, we'd like to know what's the sample complexity in terms of n, which is the domain size. So, you know, over the last 15 years, we've had great progress. We have some optimal bounds. We know a lot of problems that we didn't know 15 years ago. We can additively estimate entropy, support size, closeness of two distributions in n over log n samples. This is surprising to many communities beyond the TCS community. This was surprising out. So it's really created, in fact, I left off some citations, but that are from different communities now, so different communities are paying attention to these things. You can tell if two distributions are the same or epsilon far in L1 distance in either n to the 1/2 samples or n to the 2/3 samples, depending on what you, I mean, there's many ways to phrase this problem, so it depends how you phrase the problem. Like if you're trying to test if your distribution is uniform or any other specific distribution that you actually know, then it's n to the 1/2. But if you have samples coming in from two distributions and you're trying to figure out if they're identical or different, that's n to the 2/3. Okay, so this is something we know. There's been a lot of follow-up work. This is not an exhaustive list of references because there's been a lot of things that I forgot to add in recently. So this is already still active in the last couple of years. We can gamma multiplicatively estimate the entropy in sublinear time. So if I want a 2 approximation of the entropy, I just want within a factor of 2. Not additive, but multiplicative factor of 2. N to the 1/4 samples are enough. Okay? And there's much, much more known. So this is a very active area, even recently. So over the last 15 years, it's been studied, but over the last, say, 3-4 years, there's been sort of exponentially more papers, I would say. Okay, so now what do? Okay, you tested your distribution, you used one of these recent algorithms, and it looks good. It's pretty much okay. So you know that it's close to having whatever property you wanted, but it's, you know, that's all you know. It's only close, right? So maybe your samples aren't quite right for some reason. What are you going to do now? You want to use these samples for whatever it is you need to do next. So what's some examples of noise? So just, we all can think of examples of noise, why there's noise in our samples. I'm just going to give some other reasoning, so we, just to put some examples on the table so that we have something to think of. But maybe we've got a huge sensor network, and some of the sensors lost power and some of them went crazy, but most of them are pretty good. Okay, so, and you're trying to figure out something about whether the traffic is going up for the day or not. Okay, so the first time I made this slide, I was in Bangalore, so I used something specific to Bangalore.
You mean losing power?
Wait, no, those are the cabs from Bangalore. Yeah. We didn't lose power. There was too much power in the air that day. That was actually, okay, but that was the view. And maybe you're interested in some kind of astronomical data and you want to see if the universe is expanding or not. And some meteor shower got there in the middle and confused some of your measurements. This is actually a real example, okay? So one day I was, after I dropped my kids off at school, and I met with this friend of mine, and we were discussing what we do at work, and so I told her I work on correcting data, and she told me that, she works on, she's a social worker. She works with recovering teenage recovering drug addicts, okay? And she's doing some study, and she was telling me that, she took my advice and she sent in her paper and it got in, and now she has to go talk about it, but she's missing data. And as we said goodbye, she said, I gotta go to work, I gotta go make up some data. And I said, I can help you. Okay, so this is what we're here to do, okay? We're helping make up data. Whooping cranes. This is a paper we found where the type of error was not only the other types we talked about, but also GPS errors in location and what that does to affect your distribution. There's all kinds of ways you can have errors. And then you look at your examples from your distribution and you get something like this and you're like, well, how do I correct that? Okay, so maybe that's the way to correct it. Or maybe that's the way to correct it. So who prefers the first method? And who prefers the second method? Nobody cares. Okay. Okay, well, it seemed a few more people preferred this method. Okay, why? I mean, why did you prefer that? What? Simpler. Okay, so I actually thought that's prettier. But okay. So yeah, okay, so simpler. I mean, that's a good reason. So, what are we supposed to do? How are we going to come up with a good methodology for fixing our samples? I mean, we need to somehow make it mathematically precise. What we mean by this simpler or whatever it is we're going to use. Okay. Now, it's not like we're not the first people to look at fixing data from distributions, and it is something that's been considered in statistics, and I can't say that, okay, it's actually considered widely. There are books, there's everything. I've gotten to the point where I bought the books. I can't say I've read them all yet, but it seems from our attempts at understanding what's going on, most of what we've found so far assumes something about the data. For example, that it was supposed to be Gaussian and then it tries to fix it to be the closest Gaussian, or it does some sort of outlier removal, or and there's the names that we've found, that the buzzwords that seem to apply to this are things like imputation, missingness, and there's a whole literature on this. Okay, so the question is though, what if you don't know when you're trying to correct your data, your sample data, that actually the distribution was supposed to be Gaussian? I mean, maybe it wasn't supposed to be Gaussian. Maybe it wasn't supposed to be normal. I mean, why would you try to correct it to the nearest Gaussian? Okay, so what are we going to do? All right, so what we'd like to do is, so this is going to be a talk more about questions than answers. I have to warn you right now. It's like what we're going to do now is propose a methodology for correcting your samples. Okay, so the idea is, okay, so we need something to do, and what we'd like to do is sort of use what we've learned about testing whether a distribution is in a particular class and say, okay, I'm now going to assume that my distribution was supposed to be in a class. And what I'm going to do is correct it to a nearby member within that class. Okay? So if I can assume that it was Gaussian, I'll try to move it to the nearest Gaussian. But maybe I don't know that it's Gaussian. Maybe all I know is that it's unimodal. And in that case, I'll try to move it to the nearest unimodal distribution. Or maybe all I know is that the distribution was a k-histogram distribution. Okay? So then I'll try to move my samples to be close to the nearest k-histogram distribution. So whatever class it is that I think this data is coming from, I'm going to try to change my samples and correct them so they're closest, so that they're from a distribution of this property, and they're still close to my original samples. Okay? So that's the idea, and that's the methodology we're proposing here. Okay, so it could apply to what people have done in the past, but the idea is to be a little more general and allow other types of corrections as well. Okay, so that's what we're going to do. You're given samples of some distribution Q, and it's supposed to be epsilon close to some member of a class P. So P is a collection of distributions that have the property. Okay, P could be all unimodal distributions. Okay, and now we've tested Q and we've shown, okay, it's epsilon close in L1 distance to unimodal. All right, but now I want to correct it to be unimodal. Okay, and so that's what we're going to do. We're going to output samples of some Q prime such that Q prime is still close to our Q, but it has the property that we wanted. Q prime is going to have the property of unimodality or whatever it is that we're assuming in P. Okay, so that's the model we'd like to propose. Good? Questions, complaints? Okay, so that's the goal. All right, so now what are we going to be interested in? Because we have to do something with this. So first we're interested in what's the sample complexity per output sample of Q prime. Okay, like I'm getting samples from Q. I'm going to now try to output samples of Q prime. How many samples of Q do I need to take for each sample I put out for Q prime? Okay, so that's one kind of question we could ask. And that's mostly what I'm going to talk about for the rest of this talk, which is supposed to be over now anyway. That's okay, I don't have that much more to say. And the second question that I'm just going to say a little bit about is, what is the randomness complexity per output sample of Q? Like, okay, do you need to toss your own coins and get your own source of randomness to help yourself output Q prime? Or can you mostly use the randomness you got from Q? Okay, so this is a question kind of if you're interested in like, what are they called? Not de-randomization, but we'll talk about this later. Okay, so here's an observation. If you have an agnostic learner for a distribution class, okay, then you can get a sample corrector. And this would give you, we have agnostic learners for monotone distributions, for the class of monotone distributions. So we can get sample correctors for monotone distributions that have order log n sample complexity. So you need to take, but after you've taken order log n samples, you can put out new, you can generate according to Q prime with constant time per sample, but all of that has to be with your own new randomness. Okay, so anyway, that gives us an order log n sample complexity for monotone distributions. We can get some better things for histogram distributions if we were already promised that it's monotone. I don't really want to go into it, but just this observation alone gives you sort of an easy way of taking agnostic learners and giving something for sample correcting. Okay, so there's always, this bound you should always, this is the one you want to try to compete with. Okay, and the big, to me the big open question is, when can you be more efficient than agnostic learners? Maybe you can't ever, or maybe there are some times that you could. Okay, so we looked at the class of monotone distributions because they're sort of basic, they underlie, you can approximate many other types of distributions as kind of combinations of monotone distributions, and so this was sort of where we decided to start. It turns out that if you know that the error is tiny, you can correct it. really easily, okay? If you have access to a little bit more powerful queries, instead of just samples of the distribution, if you have cumulative distribution function queries, okay, when might you have that? Well, maybe you have tons of samples out there, like, and somebody sorted them. Okay, so you can go in and you can go into that big storage bin of samples. They're completely sorted. Then you can implement CDF queries. Okay, and another case where you can do better than the learning bound is for certain types of errors, which I'm going to call missing data errors. Okay, unfortunately, it's not likely you can beat the agnostic learning bound in general because we have a argument from Paul Valiant to say this, and that's the case of constant arbitrary error, not really small error, and you don't have extra CDF queries, and you can't make any assumptions about the error. Okay, so I just, before I go into this any further, I want to say something about how would you learn monotone distributions, because this is a really nice technique that we didn't know 15 years ago, but it was around much more than 15 years ago. We just didn't know it, and it's much better than what we recreated instead. So it's just a good thing to know. So kind of following Jelani, I'm going to spend a slide here and teach you something that if you already know, great. If you didn't know, it's only a slide. So it's good. Okay, so this cool idea of Birge buckets. Okay, what Birge said to do is let's partition the domain, and I'm now worrying about monotone distributions over the total order 1 through n. Okay, that's all I care about. And what I'm going to do is partition the domain into exponentially increasing partitions. Okay, so maybe the element 1 in the domain is in its own partition, and maybe 2 and 3 are in the next partition, and maybe 4, 5, 6, 7, maybe, I don't know what I did here, maybe 4, 5, 6 are in the next partition, but they're exponentially increasing by a 1 plus epsilon factor. Okay? So eventually you're getting to really big buckets. And now what Birge proved is that if you take the distribution, let's call it p hat, which in each partition kind of averages the elements assigned to that partition and just outputs the average value. Okay, so green was p. P hat is this red guy. The average value of just one element is just the same value. Okay, but here I've averaged elements 2 and 3, and I've given them both the same. Okay, here I've averaged 4, 5, and 6, kind of, and we've given them all the same. If this is p hat. Now, what Birge proved was that if p was actually monotone, then p hat is close to p. Okay, so p hat is uniform on each bucket, but it's got the same marginal in each bucket as p did. And if you do that, then p and p hat in L1 distance are at most epsilon. Okay, and that's by picking these buckets to be growing by a factor of 1 plus epsilon. So this is the Birge bucketing. Okay, and the beauty of this, and this is really amazing. Okay, you don't have to know anything about B. You pick these partitions obliviously. Okay, so the fact these segments of size 1 plus epsilon to the I don't depend on P at all. So you don't know what you don't know how much probability to assign to each bucket until you see P. But you already know who's going to be in each bucket before you assign P. So it's an oblivious decomposition of the domain into log n partitions. And all you need to do now is estimate the marginals in each bucket. There's only log n of them. And so you can do this very quickly. Okay? So you can estimate p hat very quickly, and you now have a great estimate of p. So that's basically how you learn in log n samples a monotone distribution. Okay. Well, I just want to point out a simple observation. Now suppose you have a distribution that's not monotone, but it's kind of, if you looked at the p hat for this distribution, if you looked at the Birge bucketing for this distribution, the marginals would be monotone. But the only error you have is within a bucket, you know? Like the marginal here is fine, it's less than this guy, but within the bucket it's all messed up. It's not monotone at all. So this would be really easy for us to fix, because what we could do is pick a sample x from p, because that's what we have access to. And instead of outputting x, I'll just output some other element chosen uniformly from x's bucket. And that will exactly give me my Birge approximation. Okay, so that's all we have to do. So somehow internally to the buckets, it's really easy to fix errors. The problem is getting the weighting right between the buckets. But you'd think, how bad can that be? There's only log n of them. Well, turns out it was harder than we expected. Okay, so, but let me call that the Birge bucket correction. Okay, so first of all, I'd like to say that if you have p that's really close to monotone, that's really close, 1 over log squared n close, okay? If it's 1 over log squared n close to monotone, we can correct this thing obliviously, and we can make it monotone. We don't have to learn anything, okay? It's constant samples per output sample. So why is that true? We're going to mix the Birge bucket correction with a slightly decreasing distribution. Because the problem with the Birge bucket correction was, even if we correct and the Birge buckets are fine, it could be that the buckets didn't actually go down. Maybe one was up higher. So what we're going to do is mix it with a distribution where there's kind of spacing, just an arbitrary distribution where there's some spacing between the buckets, and that's going to be enough. Okay, so that's all you have to do. It's you just have to work it out, and you can see that this is really all you have to do. So this little thing we can do, and we can do it obliviously. Okay, so that's one thing. But unfortunately, in general, with constant error, there's going to be a problem. So you really do need to do a little bit. So basically, we kind of hit a depressing moment. But I do want to say that if we give, I don't want to dwell on the depression here, okay? So we're going to go by this very fast and try to find something positive. And the next positive thing is, well, what if you have stronger queries? Okay, and these are the queries we talked about before. You have like a whole bin full of samples, and they're organized for you. Somebody sorted them. Okay, you don't have time to look at them all, but they're in there and they're sorted. You could think of people's buying whatever they're shopping. Somebody sorted all the shopping data or something like that, and you don't have time to look at all that, but you're trying to figure out what's going on with this distribution. Well, here we can actually get a sample corrector that uses root log n queries. So remember the learning bound was log n queries per sample. Here we can use root log n, so square root the amount per output sample. Okay, and I'll just give a sense of the idea. We're going to take, we have the Birge bucketing. It's got log n buckets. What we're going to do is group together square root log n of these buckets and call it a super bucket. So this is the first square root log n buckets, this is the next square root log n buckets, and this is the next square root log n buckets. So we're going to have square root log n super buckets, okay? And the first thing we're going to do is use the conditional distribution queries to figure out how much weight is in this set of super buckets, how much weight is in this set, and how much is in this set. And then once we figure out, okay, okay, this guy has, what did I want to do? This guy has more weight than this guy, okay? So I need to add some weight here and remove some weight here, and I need to add enough weight here so that I don't ruin it in comparison with this guy. And so there's all these things, you can do that with an LP. It's very simple, and it's only on log n numbers, square root log n numbers. So you can use an exponential algorithm, whatever you want, okay? So, but basically, we're going to remove some weight here and put it here. Okay, well, then we still have this problem in this picture that, okay, we got the marginals to be decreasing among the super buckets, but we need to get the marginals also to be decreasing among the buckets. So once we fix this, we still have these problems here. And we have this problem that goes over the border. So we need to fix this, okay? And how do we fix this? I'm not going to, I think you guys want lunch, but I will just say, you can always somehow move weight to the first bucket. You can always decide using rejection sampling. I can always say with probability, some little probability, I don't actually output according to the bucket I found. I throw some more weight to the first bucket, and that reduces. Okay. I can also increase wherever I want by taking some probability from the last few buckets. So the last few buckets I can decide, you know what, I'm never going to output according to those, and I'm going to use that probability to increase wherever I need it. Okay, so that's something you can always do, but the rest of the fix we do has to be done quickly and on the fly. And I only have square root log n queries, so pretty much what can I do? I can look at the buckets within my super bucket, maybe I can look at the buckets in the preceding super bucket and maybe the following super bucket, but I can't look at all the buckets. But it turns out that you can do this by just looking at your preceding bucket and the next bucket. And what we keep track of is sort of the average weights of each super bucket. The reweighting makes sure that these average weights of each super bucket were monotone. So we started with average weights that were monotone. And now these average weights AI fix the AIs. They used to be the average weights after the first set of fixing. Now fix them, don't change these AIs. And what we're going to do is keep those as a way of making sure that that one super bucket doesn't go above the next super bucket. Okay, so we call it a water filling scheme, but never mind. It's basically, it turns out that you can take, let me show you the picture. You can take some of this and fill it in here, as long as this doesn't get above the A sub I for this guy. And when you run out of room to fill it in here, you throw it in here. Okay? How do you do that? Again, using a lot of accept-reject mechanisms. You know this is too big, so with some probability you throw it over here. With some probability you throw it over here. But you don't throw too much over here because this should never get above the A sub I for this bucket. Okay? So that's kind of the idea of what we do. And then you have to show that you can do this, that you don't create anything illegal. So that's in the paper. And we'll just leave that, okay? So that can be done, and it's, all right. I want to mention one other thing. What happens when you have missing data errors? And here, let's assume that, you've got like something, just these PIs, you never saw them. Okay, it's a consecutive set of P sub i's, which you just never saw. Okay, so what happens in that case? Well, it turns out that you can get really efficient sample correctors in this case. In fact, it's kind of cheating because you sort of learn the missing part. You learn it, you don't actually have to learn it very well. You can use the Dvoretsky-Kiefer-Wolfovich, the DKW inequalities, and you can learn this quite quickly. So there are certain cases, and I think that this is another area for further study. I mean, I don't think we should come up with every possible error model and study every single one, but it seems like there would be some reasonable error models of missing data. I mean, there are in statistics whole books on missing data. So it seems that this would be a great area to continue looking at. Okay, there are some other relationships between these sample correctors. If you have a sample corrector and a learner, that immediately gives you an agnostic learner. So this could be a way of empowering our learners. I mean, if many times we have learners, but we don't have agnostic learners. But this could be like an alternative way of taking a situation where we have a learner, and instead of, and maybe, I don't know if it'll be easier, but it's another way of thinking about trying to make our learners agnostic. Okay, another situation which is actually very analogous to what happens in the property testing world, we call it Brzekerski's result. Brzekerski showed that in the property testing world, if you have a corrector and some kind of, basically if you have a certain kind of corrector and a tester, then you can get a tolerant tester. So similarly here, if you have a sample corrector and a distance approximator between two distributions, and then also a tester for this property, then you get a tolerant tester. The problem is that this distance approximation thing with distributions can be really awful. Like with data, in the property testing world, you're testing distance between data. Sometimes that's just constant time. It's not a big deal. Here, it can be really bad because you're only seeing samples. But there are certain cases, such as in monotone distributions, where you can do distance approximation quite quickly. So it may be a way of getting tolerant testers. It's certainly something to think about when you're looking for tolerant testers or agnostic learners. Okay, I'll just say a word about randomness scarcity. Can you do this correction using little randomness of our own? This question is a generalization of the von Neumann corrector of the biased coin. You can compare this to extractors. It's not the same, though. It's not the same model. And it turns out that for monotone distributions, yes, you can. Okay. All right, so what next for correction? And I think this is the big question. When is correcting easier than learning as a general field? I think we don't have a lot of answers yet, but this is very new. And the hope is that if people keep looking at it, we'll just find more and more cases where this is interesting. That's it.
Questions?